A theory of everything is a really big idea. It's the dream of many physicists. Imagine one single set of rules, one big equation maybe, something that explains everything in the universe. All the forces, all the particles, why they act the way they do. From the smallest bits of matter to the biggest galaxies. It's a grand quest. But then there's the question, can we actually prove such a theory is correct? And what does proof even mean when we talk about science? It's not as simple as it sounds. It makes you think about how we know anything at all about the universe. So, let's talk about what a theory of everything really is. Think about what we already know. We have two main powerful theories in physics. One is general relativity. This is Einstein's idea. It tells us about gravity. It explains how big things like planets, stars, and galaxies move. It explains how space and time bend because of mass and energy. It works incredibly well for huge things and fast things. We use it to guide spacecraft and understand the cosmos. Then we have quantum mechanics. This theory tells us about the tiny stuff, atoms, electrons, light, quarks, the incredibly small particles that make up everything. It explains how these tiny things behave. It's weird and doesn't make intuitive sense sometimes. Particles can be in two places at once, they can be connected in strange ways, but it also works incredibly well. It powers our computers and lasers. The problem is, these two theories don't like each other. They work great in their own areas, but if you try to use them together in extreme places, like inside a black hole or at the very beginning of the Big Bang, they break down. They give nonsensical answers, they just don't fit into one picture. A theory of everything would fix this. It would bring general relativity and quantum mechanics together. It would be one unified theory for everything. It would explain gravity and the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force. These are the forces that hold atoms together and make light work. A TOE would explain all particles we know. It might even explain things we don't understand yet, like dark matter and dark energy, which seem to make up most of the universe. Some smart people have already proposed ideas for what a TOE might look like. String theory is one of the most famous. It suggests that all particles aren't tiny points, but really tiny vibrating strings. Different vibrations of these strings are different particles. This idea naturally includes gravity. Another idea is loop quantum gravity. This theory suggests that space and time themselves are not smooth, but lumpy, made of tiny discrete units. These are just some of the big ideas trying to bridge the gap. What would a 2E do? It would give us the deepest possible understanding of reality. It would let us calculate the properties of particles from first principles. It might even tell us why the universe started. It's the ultimate goal of physics. Now, let's talk about proof. This is where it gets tricky. When a mathematician talks about proof, they mean something very specific. A mathematical proof starts with a set of assumptions called axioms. Then, through pure logic, step by step, they show that something must be true. It's absolutely certain. Once proven, it's proven forever. 2 plus 2 will always equal 4. The angles in a triangle on a flat surface will always add up to 180 degrees. This kind of proof is absolute. But science is different. Science doesn't prove things in the absolute mathematical way. In science, we don't ever say something is 100% absolutely, beyond a shadow of a doubt proven. What we do instead is gather evidence. We make observations, we form hypotheses, which are educated guesses. We make predictions based on those hypotheses, and then we do experiments to see if those predictions come true. Think about gravity again. Isaac Newton came up with a theory of gravity. It explained why apples fall and why planets orbit the sun. His predictions matched what we saw. We were very, very confident in his theory for hundreds of years. But then Einstein came along with general relativity. Einstein's theory made slightly different predictions in extreme situations. For example, it predicted that light would bend around massive objects, and it predicted tiny wobbles in the orbit of Mercury. When scientists tested these predictions, Einstein's theory was found to be more accurate. So, Newton's theory wasn't wrong in a simple way. It was incredibly useful and mostly accurate. But Einstein's theory was more accurate and worked in more places. This is how science progresses. We refine, improve, and sometimes replace older theories with newer, better ones. We never say a theory is proven correct forever. Instead, we say it's strongly supported by evidence, or has withstood rigorous testing. A key idea in science is falsifiability. This comes from a philosopher named Karl Popper. He said that for a theory to be scientific, it must be possible to prove it wrong. If there's no way to test a theory, no observation or experiment that could ever show it's incorrect, then it's not really science. It's more like a belief or a philosophy. This is a big deal for a theory of everything. The confidence we have in a scientific theory grows with more and more evidence. When a theory predicts something we didn't expect, and then we go out and observe it, that's incredibly powerful. For example, general relativity predicted gravitational waves, ripples in space-time itself. For decades, we couldn't detect them, but recently we did. That made our confidence in Einstein's theory even stronger. The same happened with the Higgs boson particle. The standard model of particle physics predicted it, and years later, we found it with the Large Hadron Collider. These are the gold standards of scientific confirmation, so if a theory of everything is ever found, we won't prove it correct in the mathematical sense. We would need to gather such an overwhelming amount of evidence that we become extremely confident in it. It would have to explain everything we already know, and most importantly, would have to make new testable predictions. Predictions that are then confirmed by experiments or observations, but there are huge challenges to doing this for a theory of everything. These challenges make it very hard to get to that level of overwhelming confidence. One of the biggest problems is the energy scales involved. Many of the interesting effects predicted by a 2e, the places where we'd really see it in action, might only happen at incredibly high energies. We're talking about energies far, far beyond what our current particle accelerators can reach. The Planck scale, for example, is where physicists expect quantum gravity effects to become obvious. This energy level is so high, it's almost impossible to imagine. It's like trying to build a machine as big as a galaxy to smash particles together. We just don't have the technology. We might never have the technology. And even if there are effects at lower energies, they might be incredibly tiny. So small that they'd be almost impossible to detect. They could be swamped by all the other noise and effects we already see. It would be like trying to hear a whisper in the middle of a rock concert. Another big challenge is the lack of specific testable predictions from some of the current TOE candidates. Take string theory again. It's a beautiful mathematical framework. It looks like it could unify everything. But it makes very few predictions that we can actually test right now. Many of its predictions are about particles we haven't seen or extra dimensions that are curled up so small we can't detect them directly. And it suggests there might be a landscape of an enormous number of possible universes, each with slightly different physics. If there are so many possibilities, how do you know which one describes our universe? How do you make a specific, unique prediction that would confirm it? This makes it really hard to falsify the theory, which, as we discussed, is a core part of science. This landscape problem is a serious philosophical hurdle. If a theory can describe almost any universe, then it's hard to say it specifically predicts our universe. It becomes less about predicting new things and more about explaining what already exists, which isn't as strong for scientific confirmation. Then there are just general philosophical problems. What if we found a theory that mathematically explained everything perfectly, but it never made any new testable predictions? If it just explained away all the mysteries without giving us a way to check it further, would it still be science? Or would it be more like a very elegant philosophy? Most scientists would say it needs to be testable. And we have to consider the limits of our perception and our tools. Are there fundamental limits to what we can ever observe or understand about the universe? Maybe some aspects of a TOE are just beyond our human capacity to grasp or detect, no matter how smart we get or how good our technology becomes. Also, some theories rely on the anthropic principle. This idea suggests that the universe's constants, like the strength of gravity or the mass of an electron, are exactly what they are, because if they were different, we wouldn't be here to observe them. This might explain why the universe seems so fine-tuned for life, but it's not a scientific prediction you can test. It's more of an explanation after the fact. It doesn't allow for a clear experiment to prove or disprove it. And that makes it problematic for scientific proof. So, given all these difficulties, what would success look like for a theory of everything? How would we know we're on the right track even if absolute proof is impossible? Success would mean that the theory consistently and elegantly unites general relativity and quantum mechanics. It would remove all the mathematical inconsistencies and infinities that pop up when we try to combine them now. It would just work beautifully, without any patched up bits. It would explain all the known fundamental particles and forces. The standard model, our current best theory of particles, would naturally emerge from this deeper TOE. It wouldn't just be a list of particles. The TOE would tell us why those particles exist and have the properties they do. It would also explain the values of fundamental constants. Right now, things like the mass of an electron or the strength of gravity are just numbers we measure. They seem arbitrary. A TOE would ideally tell us why those numbers are what they are. It would derive them from its basic principles, and a successful TE would finally explain dark matter and dark energy. These are two of the biggest mysteries in physics right now. They make up about 95% of the universe, but we don't know what they are. A2E would have to provide a clear, testable explanation for them. But the most crucial part for Proving it scientifically is this: it must make novel, precise, testable predictions that are then verified by experiment. Not just explaining things we already know, but predicting entirely new phenomena that we then go out and find. For example, a TOE might predict the existence of a new particle, different from anything in our current standard model. If we then build an experiment and detect that particle, that would be a huge victory. Or it might predict a tiny deviation from general relativity or quantum mechanics at certain scales. If we can measure that deviation, that would be strong evidence. It could even predict subtle effects of extra dimensions or different kinds of gravity that we could indirectly detect through precise measurements. Beyond testable predictions, a TOE would likely possess incredible mathematical elegance and internal consistency. To physicists, a theory that is simple, beautiful, and holds together perfectly is very compelling. General relativity has this quality: it just feels right. But while beauty and elegance are wonderful, they are not evidence. And evidence has to come from observations of the real world. The theory would also need to be universal. It should hold true everywhere in the universe, from the smallest point in a black hole to the most distant galaxy. It would resolve all the current paradoxes and inconsistencies that plague physics. No more weirdness that we can't explain. The strongest form of scientific confirmation for a 2E would be if it predicts things we don't expect at all. Something completely surprising, but that we find it exactly as predicted. This moves beyond just explaining the known to actually foretelling the unknown. That kind of predictive power is what separates a great scientific theory from just a good one. Of course, there's always the chance that we might get a theory that works for everything we can ever measure, everything we can ever observe, but it's not truly complete. Maybe it still has some unknown bits that are forever beyond our reach. Is that a theory of everything? It depends on how strict you are with the definition. For many physicists, if it works for all observable phenomena, that's close enough. So, to come back to the original question, can we prove a theory of everything is correct? No, not in the absolute logical sense of a mathematical proof. Science doesn't work that way. We can't definitively say this is 100% correct and will never change. But what we can do and what we strive for is to gather so much evidence, to perform so many experiments, to make so many confirmed predictions that we become incredibly, overwhelmingly confident that it is correct. We would trust it implicitly. We would use it to guide our understanding of everything. It would be the crowning achievement of centuries of scientific inquiry. The path to getting there is unbelievably hard. It needs new ways of thinking, new theoretical breakthroughs, and likely entirely new technologies that we can't even dream of right now. It might require experiments far grander than anything we've ever conceived, and there's always the possibility that even if we find a theory that explains everything we can currently observe, a tiny flaw might show up centuries later. A small, unexpected observation that forces us to refine it, or even replace it, just like Einstein refined Newton. That's how science usually works. It's an ongoing process, not a finish line. But the quest itself, the pursuit of a theory of everything, is incredibly valuable. It pushes our understanding to its limits. It drives the development of new technologies. It makes us ask the deepest questions about the nature of reality. It forces us to stretch our minds. Even if we never reach an absolute undeniable proof, the journey to find it too is one of humanity's greatest adventures. It's a continuous exploration of the universe and of our place within it. It might be a never-ending chase, like a horizon we keep moving towards but never quite reach. But that chase, that relentless search for deeper truth, is what keeps science alive and vibrant. And that's pretty amazing to think about.